Yeah, so thanks for the introduction. Yeah, it's been a very nice conference. It's quite an honor to speak here, especially maybe so for me because I think of myself as a bit of an outsider to the subject. I'm definitely a geometric analyst, and the philosophy of the subject can pretty much be summed up by the words "show me the estimate." I mean, you have some PE you care about, you have some situation, you try to prove some a priori estimates for this PE. And in my case, I had an equation which is, well, motivated, appears in some math physics literature a long time ago, and which we sort of rediscovered in a way from some questions in complex geometry. But the more I studied it, the more it became clear that it was very much tied up with generalized geometry. And so I guess in keeping with the religious theme of the week, you'd say that I'm a convert, and there's no more fervent believer than a convert. So here we go. I could more or less skip my first 5 slides, I think. It's all been covered nicely a few times, but let me just say a very few words. So here I repeat, I guess the laser pointer doesn't work. Okay. So I just repeat here briefly the bi-Hermitian formulation of generalized Taylor geometry, which, again, I think phrased this way, I mean, this is how it was first discovered in this paper of Gates, Hull, and Rochek on these studies of supersymmetric sigma models. So Marco gave a great explanation of this. And I mean, the first time I saw this, I saw it in this form. I thought, who ever thought of this? I mean, it seemed like the strangest thing I'd ever seen. But luckily, of course, by the time I came to it, we already had, in a sense, a much more natural geometric explanation of what this structure really is. But they were essentially ignored, as far as I know, until Marco and Nigel's discovery of generalized complex geometry. So again, this was all discussed in Alexander's talk and also in other talks. It's a, of course, really important subcase of the general subject of generalized geometry, which at least the way I see it, is a very sprawling subject with sort of diverse origins in many fields, more than one place in math physics, dynamics, this Weinstein school that Marco alluded to, complex geometry, etc. And so again, Alexander introduced these, but I just repeat the 2 key objects underpinning generalized Taylor geometry. Well, first of all, you work on the tangent model plus the cotangent bundle, and you have this neutral inner product, which I expressed there. So X is always a vector. Roman letters are vectors, and Greek letters are covectors. So you have this neutral inner product, and then there's this Dorfman bracket. And again, the specifics of the Dorfman bracket aren't maybe, I mean, exactly relevant if you've never seen it before. Maybe the key point is that the tangent vector, tangent vector spits out as just the Lie bracket of the 2 vectors you're given, and it can also be twisted by a closed reform. So this is a natural thing to do with the Dorfman bracket. Okay, and then on this background, a generalized complex structure is the usual almost complex structure on the bundle E, which satisfies an algebraic condition. So it's orthogonal with respect to the neutral inner product, and then it has an integrability condition, which is that the I eigenbundle is closed under the Dorfman bracket. And of course, the 2 key examples are that of a symplectic form and a traditional complex structure, where you can just write down the endomorphisms here, as I did. And then kind of the beautiful fact is that this Dorfman integrability, in the case of the symplectic type 1, is exactly equivalent to omega being closed. And in the complex type 1 is exactly equivalent to classical integrability. So I think this was part of what sort of was so exciting initially in the physics world with the advent of this work, because it sort of naturally, especially in view of mirror symmetry, right, that it sort of naturally blends these 2 structures, which I thought to be blended anyway. Okay, but so yeah, so again, keeping with the theme of the week, I'll just mention or show us all this this paper. So they were really, I described it slightly anachronistically. They were really first discovered in this paper of Nigel's titled "Generalized Calabi-Yau manifolds," which is well, and I'll explain his point of view on generalized complex structures in the next slide. And kind of amazingly, as I understand it from Nigel, he sort of stumbled upon me by studying some exceptional cases that arose in the classification of symplectic polynomial groups, which is, to my mind, kind of amazing and testament to the subtlety of mathematics and Nigel's ability to discern that subtlety. And as far as I know, that sort of link has not really been, I don't know, further explored or used in generalized complex geometry. And maybe I just say one thing. I think as amazing and sort of far-reaching as this paper is, immersively, the terminology, it did not last. My theorem statements would be completely incomprehensible if I had to call them generalized Calabi-Yau structures. I'd be talking about generalized Calabi-Yau manifolds or something. Okay, so generalized Calabi-Yau structure is really generalized complex structure. That's really what we call it now, more or less. But so let me just briefly say my sort of original point of view, how they were discovered, is from the spinor point of view. So you can sort of recast this definition using spinor. So elements of P plus C star act on differential forms using interior product and wedge product, as I write there. And then again, sort of suppressing, and that just gives like an intrinsic sort of algebraic characterization of what the correct spinors are. But let me just sort of skip that and say that a spinor can be said to define a generalized complex structure if the I eigenbundle is exactly the kernel of this action against some spinor psi. Okay, and if that's the case, we'll call the generalized complex structure J psi. Okay. And then integrability condition for J, if it is expressed in terms of some spinor psi, is equivalent to the existence of a section x plus c, such that if you take this twisted exterior derivative, so dh naught psi should just be the action of this section on psi. Okay. And of course, the special case is when the spinor is simply closed. Okay. And I guess it should be emphasized that it's not even the case locally that you can always describe a generalized Taylor structure by a closed spinor. In fact, this is sort of crucial for various aspects to come, and it's tied in with the degeneracy locus of the associated quantum. But okay, so yeah, so with this language of generalized complex geometry, Marco, of course, gave his this beautiful description of generalized Taylor geometry in his thesis. So you could think of it as an integrable reduction of the structure group of this bundle E to its maximal compact subgroup UN cross UN. So this is something much more natural, I think, to a modern differential geometry to do. And in any case, the explicit description of this relationship is in terms of a pair of generalized complex structures which satisfy these two algebraic conditions, one that they commute as endomorphisms, and then this positivity condition, this open positivity condition, and and the integrability, of course. So the integrability of J1 and J2 sort of recaptures this somewhat strange looking equation from the bi-Hermitian point of view. Okay, and of course, again, the specifics of this formula are maybe not so important than just that there is one. There's this very explicit map between the bi-Hermitian data and these generalized complex structures. Okay. So yeah, so the point of the talk today is to sort of talk about one aspect of what Vesti talked about, which is this kind of broad Calabi type question that we're trying to understand for generalized Taylor geometry. So the basic question in Calabi's work is, what is the canonical representative of a Taylor class? And so very generally, we can ask the same question. So without defining yet, what is a generalized Taylor class? It's actually quite a subtle thing. That was pretty much the whole topic of Marco's talk, in a sense. We can still ask this question: what is a canonical representative of a generalized Taylor class? And of course, this question has been essentially the dominant theme of Taylor geometry for at least 70 years, with the most sort of fundamental key point being Yau's theorem, which I state here. So if you have a compact Taylor manifold with vanishing first Chern class, there's this unique Ricci flat metric in that class. Okay. And let me just to sort of set the stage, just recall the rudimentary aspects of Yau's theorem that sort of make it work. So you sort of start with a global Beatty-Barr lemma. So the point is you can understand metrics in the same Taylor class as being related by a Taylor potential in this way. And then, of course, the key point that kind of makes it so tractable versus other special holonomial questions is that you get this scalar reduced PDE. So to solve for a Ricci flat metric, it suffices to solve this Monge-Ampere equation. So here I've cheated a little bit, and I've already assumed the existence of a holomorphic volume form. That's the big omega. Okay, so this equation, if you have that this particular scalar is constant, the metric is Ricci flat. Okay, and then of course Yau gave an elliptic PDE proof of his result, but more relevant to what I'll talk about today, Cao reproved the Calabi-Yau theorem using Kahler-Ricci flow. So okay, so similarly, and I'll say specifically what he proved later, but the point is you can start Kahler-Ricci flow with any metric if the first term class is 0, and it will exist for all time, and it will converge to the Calabi-Yau feature. Okay? So it gives a different proof of Yau scale. Okay, so I have to say what is a generalized Kähler class? And again, here Nigel's contribution of understanding the existence of this Poisson tensor associated to a generalized Kähler structure is key. So here I write down the formula again. So again, Ruxandra wrote this down. So sigma is 1/2 bracket IJG inverse. And I'm gonna just take a very simplistic approach to what is the generalized Kähler class. So there's work going all the way back to Joyce, Marco, Nigel, who sort of we're trying to understand generally, I think, deformations of generalized Kähler structure, but sort of look hard at what they did, and it's not so hard to write down what I call canonical deformations. Okay, so here I write it purely in terms of the bidimension data. So like G, B, I, and J. I will be fixed, that's a choice, but it's sort of equivalent up to gauge. You can always fix either I or J. And you kind of see what looks like, so you vary G plus BI by DDCJF, which is kind of like varying a Kähler metric by a Kähler potential. But of course, the J is also time dependent, and the J is flowing by this particular endomorphism. So it's sigma acting on DDCJF. But more precisely, you're pulling back J by a family of sigma Hamiltonian diffeomorphisms. That's really what this is. Okay, I think Vesky probably wrote something like this down. And you can also, of course, express it in terms of the generalized objects as well, which I just do here. It's naturally sort of infinitesimal B field action by some closed form K. Okay. Yeah, and then I'll give a caveman definition of what is a generalized Kähler class. It's just an equivalence class under canonical deformations. Now, in all the examples that you can, I mean, this really is the same as what Marco was talking about. It's just that I don't know what a double stack is. To me, it sounds like a sandwich, but so, I mean, all due respect. But yeah, in any case, yeah, this is a very by-hands definition of what it is. Yeah, so I've given this very kind of low-tech definition. So it's literally just an equivalence class under this type of deformation. Okay. So in particular here, I'm kind of sneaking under the rug, at least in this definition. It's sort of obvious the way I defined it. It's trivial that it's connected, for instance, right? Because it's just given by paths. Whereas actually in the symplectic type case, Vesky gave a pretty down-to-earth description of what it is without assuming connectedness. But of course, there you don't know a priori, is it actually connected? This class of objects that he wrote down, you can give a kind of a priori definition of the objects you're talking about, which I don't do here, right? But then you don't actually know if it's actually even connected. Okay. Okay. But so if that's oh yeah, sorry, let me just quickly explain what is happening in the case when sigma is non-degenerate, because this kind of captures, in a sense, the new features and is a bit simpler to see. So in the case of Poisson tensor is invertible, I'll call big omega here the inverse, which is the real part of a holomorphic symplectic form, sort of in both ways with respect to I and J. And you can take some one parameter family of functions, ft, and define the omega Hamiltonian vector fields, and then let phi t be the family of associated Hamiltonian diffeomorphisms. And then you get your generalized Kähler structure by fixing I, pulling back J, and then considering big omega as a fixed part of the data. And then the point is you can recover the metric algebraically from those three things. Okay, so basically you're letting this group of Hamiltonian diffeomorphisms act on one of the complex structures, and Well, the point is the metric is not simply being pulled back. Okay, so the metric is recovered from this pullback data. Okay, and this is the same as what I described in the previous slide in this special case. Okay, so yeah, and it just sort of underscores, just to emphasize that the generalized Taylor class has no linear structure. Okay, I just say it for like the third time now. So there's no linear structure, and so there's no, as far as I know, kind of description of a generalized Taylor structure, like in terms of a base structure, far away from the base point. So again, this is sort of step one of Yau's theorem: is take any metric in the Kähler class and sort of relate it to some base metric in terms of a potential function. So that's not really possible here. Okay. Yeah, and so okay, if we have some understanding of what is a generalized Kähler class, I now have to define what do I mean by Calabi-Yau? What do I mean by what kind of PDE am I going to impose? And so again, here I'm thinking about the spinor point of view on generalized complex structures. So if I have two spinors phi and psi, I can define the so-called Mukai pairing, which I take the wedge product of phi and psi. The S is some sign. We don't have to worry about that. So S is some sign on the, depending on the even and odd parity of the degree of psi. So you basically take the wedge product, take the top degree form. Okay. And so if we have a generalized scalar structure defined by two spinors psi1 and psi2, Marco in his thesis defines what he calls the generalized Calabi-Yau equation. So you take the Mukai pairing of psi1 with psi1 bar, you divide by psi2 with psi2 bar, you take minus log, and call that phi. And so what he calls Calabi-Yau equation is that this quantity phi should be constant. I don't really know how he discerned this, other than that somehow using the Mukai pairing to define a volume form is a natural thing to do. I think maybe there's some precursors in physics. But in any case, I'll show you that it's definitely a meaningful thing to do in just a second. So we can at least now ask something like a Calabi-Yau question a bit more precisely. So if we're given J psi1, psi2 as above, can we find a solution to this generalized Calabi-Yau equation in the generalized Taylor class of this structure? Okay, so we can ask a bit more precise a question. Okay, but sort of before doing that, I want to kind of unpack a little bit what is really the meaning of this phi equals constant equation, because I think it's a bit abstract at this point. And so to do that, I'll use the Bismuth connections. Okay, so these also have showed up already this week. So for any Hermitian structure, you have many Hermitian connections, and the most important one here is this so-called Bismuth connection. So here H is this H0 plus CB. It's the same H as always. And so there's two complex structures, so there's two Bismuth connections, and the torsions, because of the generalized scalar relation, are just plus and minus H. Okay? These have curvatures I call omega I and omega J, and then they have what I'll call Bismuth-Ricci forms. So they have natural representatives of C1. So you take omega I, you sort of contract the endomorphism part with I, factor 1/2, we call that rho I, similarly J. Okay, so we have these two Bismuth-Ricci forms, rho I and rho J. So yeah, these are closed forms, which represents the first term classes. So a key sort of starting point for our results is this following transgression formula. So this part is joint work with Bessie, Shin-Fu, and Yuri Ustinovsky. So given a generalized Kähler structure, J psi1, psi2, and here I probably should have emphasized this a bit. I'm actually assuming here the stronger condition that psi1 and psi2 are actually closed, not just interval, they're actually closed. Then the I Kähler form, the I Bismuth-Ricci form is -1/2 EJ d5. That's not a typo. Rho I is not I11, it's J11. And then rho J is -1/2 dId5. Okay, and again, rho J is I11. Okay, so that's how that works. So in particular, if phi is constant, then you have the vanishing of these Bismuth-Ricci forms. You have an Einstein type equation, okay, coming out of this Calabi-Yau type equation, right? And you might think, why am I bothering to mention this? This is like a one-line calculation in Kähler geometry. But it actually turns out to be kind of subtle. to prove this. And I will explain the proof because it's flattering to Nigel. So to prove even this basic formula, and actually a lot of the formulas that I'll mention, we have to use this subtle approximation argument. And I don't really know a better way to do it. And I can sort of explain why it's necessary at the end. So we fix generalized Kähler structures that are both of even type. This is not so important at the moment. Then near any point where they both have locally constant type, and again, we can just think of this as being in the generic locus of the Poisson tensor, so not in the degeneracy locus of the Poisson tensor. Then there exists some closed spinors defining J1 and J2 locally near this point, and then a sequence of non-degenerate generalized Kähler structures which approximate the given one. And so this is non-degenerate in the sense that the Poisson tensor is invertible. Okay. So you can find this sequence of non-degenerate structures which limit to the starting points, as we said. Okay. How do we prove this? Well, maybe before proving it, let me just say why it matters. The point is, in trying to understand this quantity phi, right, we use this Mukai pairing, which requires some underlying knowledge of the spinors defining a generalized complex structure. Now, like in the Kähler case, what does that mean? So if the Kähler case sitting inside generalized Kähler geometry, well, you have a Kähler form, that's one of your generalized Kähler, and then the other one is just a complex type. And well, you pick local complex coordinates for J, and then you have an explicit description of the other spinor, that's omega, and then it's very easy to then just do the calculation. But the point is here, you kind of don't, there's not really an obvious set of coordinates. You kind of have to, you have this mixture of these two complex structures, and you kind of need to pick complex coordinates for both, and they don't really play nicely with each other. So we need a structure where the spinor, the underlying defining spinor, is very explicit in terms of the bi-Hermitian data. And that's what is the case for the non-degenerate structures. You can just flat out write down what the spinors are. So this is why this is useful in finding these formulas. But in any case, the way we prove this starting point is Marco's Darboux theorem that he proves in his thesis. So locally, you can write a generalized complex structure as like a direct sum of a complex and symplectic type. And then here we use Nigel's like very key observation in the first paper, which is that you can deform a complex type generalized complex structure into a symplectic type one. So fairly explicitly, it looks like this. So here, big omega is a holomorphic volume form of even degree, at least even degree. And the point is then, like locally, you can express that as the top as the k power of a symplectic form. Okay, so this is this kind of complex symplectic duality that he observed, and this is literally what we do. We literally have this sort of complex leaf, and we sort of move the spinor by making it, by understanding the volume form, defining it by a symplectic form. Okay, and this is what makes both of the structures symplectic type everywhere and makes the whole structure a non-degenerate. Okay, and then, yeah, sorry, there's one more technical ingredient. So we deform one of the generalized complex structures in this way to make it symplectic type. And then we use this Goto, like Kodaira-Spencer type stability theorem. So Goto proved this general theorem that of the type where if you deform one of the generalized complex structures with a generalized Kähler structure, you can deform the other one to match. Okay, so we prove like a local version of this stability, because again, the whole argument is local, so we have to do some kind of boundary value PDEs. But in any case, we prove a local version of this, which also in a key way uses Marco's Hodge decomposition, which holds the generalized Kähler structure. Okay, so yeah. Okay, but so with that transgression formula at hand, and well, another formula which I'll state, we can actually prove the following theorem. So a compact, so here I generalize Calabi-Yau geometry. So here I mean a generalized Kähler structure defined by closed sphere spinors that satisfies the Calabi-Yau equation. Okay. Well, unfortunately, they satisfy that Gi and Gj are already Kähler-Ricci flat. So and they're furthermore unique in their generalized Kähler class. Okay, so let me just briefly describe the proof. So the proof exploits what I call these like partial Ricci potentials. So you have these defining spinors psi I, and to get this Ricci potential, we kind of compare them to each other. Here, we compare them to the Riemannian volume. Okay, we call those functions psi I, and then phi is recovered as the difference of the two. And then it turns out that if you have that p is constant, then you get the following elliptic PDE for this function psi. So minus Laplace psi1 plus norm d psi1 squared is 1/6 norm h squared. So this magically spits out, and this is actually known as like a Dilettino equation in string theory literature. In any case, by strong maximum principle, the psi1 is constant, and then therefore h vanishes. Okay, so it's Kahler and Kahler-Calabi-Yau, and then the uniqueness basically follows by showing that the underlying Kahler classes are determined by the twisted cohomology classes of the spinors, and this uses the Bogel-Bogomolov-Yau transition. Okay, so yeah, maybe I just pause for a second. So this might seem very disappointing. Why did I even give this talk? I mean, go through all this pain to define these structures, and then it turns out that they're only Kahler, Calabi-Yau. Okay, but that's not, of course, the whole story. So let me now turn to, again, this example, which came up a few times already, the standard Hopf surface, which I'll describe it in a slightly different way, but it's exactly the geometry Marco described. This is exactly coming from the like Lie group description he gave. But in any case, if you take C2 minus the origin, then quotient by the standard Z action given by dilation of the two factors by a factor of 2, that's diffeomorphic to S3 cross S1. It inherits a complex structure from that on C2. And then you can define the other complex structure J by pulling back I by a certain map on C2. And again, I mean, it might not seem obvious, but this is just like a choice of right invariant complex structure, whereas I is the left invariant one. In any case, it's basically inversion through the unit sphere and then some further reflection. That's all it is. Okay, and then the metric is just, well, it's like a cylindrical metric on C2 minus the origin. And then once you take the quotient, you just get the standard metric on S3 plus metric on S1. Then this data is generalized Kahler, and moreover, it's Bislett-Ricci flat. In fact, it's actually, both of the Bismuth connections are in fact flat. So this is actually the canonical example of, so there's a more general question of like, what are the flat Bismuth connections with, flat Riemannian connections with skew symmetric torsion. And the only new examples that you see are compact semi-simple V groups. And this is such an example. And it's moreover generalized Kahler. Okay. And the Poisson tensor you can compute. And this is what it is. So it's like Z1, Z2, del Z1, ledge del Z2. And the point is you have this degeneracy loci, so it degenerates on the two elliptic curves, Z10, Z20. This is where I is equal to plus or minus J. And so, well, the results I described, this kind of description of the geometry I described, like doesn't really quite apply because you don't even have closed spinors near this loci, okay? Nonetheless, they are Bislett-Ricci flat. And I think we should consider these. I mean, if we're going to develop a general theory of sort of Calabi-Yau geometries in this setting, surely this should count, I think. And so, so somehow we need to do a bit more to capture this example. Okay, so there's no global spinorial description here. All right, so I finally turn now, we see a bit, what are these like generalized Calabi-Yau geometries? We need some general PDE tool for trying to construct them, okay? So we sort of take a step back and just look at this field strength equation. So not really this reduced equation of phi equals constant of Markov, but just the more general kind of Einstein type equation. So let's just look at rho I equals 0. So you can do a computation and see that this is what you get. So Ricci here is just the usual Ricci of the metric. H squared, I define there, it's just the natural symmetric 2 tensor built from H. D star H is exactly what you think it is. And then we get these extra gauge terms in the equation which are generated by the Lie form. So theta I is I V star omega. This is called the Lie form. So this is the one form that's sort of some measure of the non-Kählerness of the structure. And so what you see is this kind of Einstein type equation modified by the 3 form, and then it also has this gauge type term arising from theta I. In fact, I didn't realize this until fairly recently, but like those two terms together are exactly a generalized gauge transformation, or an infinitesimal generalized gauge transformation. Okay, so these equations, but if I ignore the gauge term, so just ignore the Lie derivative term and the d nabla I theta I term, these are more or less Euler-Lagrange equations for the so-called string effective action. Okay, so this action appears in Polchinski's book, and I think it goes back quite a long way in math physics. So here I'm integrating, well, I have an extra parameter, this function f. So this is sort of the dilaton, and it's plays some subtle role in the story. Basically, you're integrating, so you fix the metric, the 3 form, and the function f. You integrate r minus 1/12 norm h squared plus twice the plus f minus norm grad squared, and you integrate against this weighted volume. Okay, and it probably went by pretty fast in Vesti's talk, but this is exactly the sort of generalized scalar curvature. He had a different normalization for the h term, but it's the same. Okay, and there in the case he was considering, the dilaton was exactly the relationship between the like symplectic volume form and the Riemannian volume form. But more generally, it's just kind of a free parameter that you have to sort of discern in some way. Okay. Yeah. Yeah, and so, well, again, this is not really how I came to the subject, but the gradient flow of this functional, at least in the generalized Kähler setting, is what I'll call, that's the generalized Kahler-Ricci flow. Okay. And this, it turns out, will be a good tool for constructing generalized Calabi-Yau geometries. Okay, so let me say now, what is generalized Kahler-Ricci flow, finally? So yeah, here, it's a one parameter family of metrics, 2 forms, and then the 2 complex structures, I and J, and they satisfy the following PDE. Okay, so what can we say about this? So the metric is evolving by Ricci flow, but coupled to H. The B field is evolving by minus C star H. So H, it turns out, is basically evolving by the natural heat flow with respect to the time-dependent metric. Remember, for me, the H is the background H plus dB. Okay, but then you also have these 2 equations for the complex structure. So both of the complex structures are also moving. By gauge terms, they're evolving by Lie derivatives, but they are moving. And it's important to notice that the 2 gauge terms are, of course, different. So I is evolving by the pullback by theta I, and J is evolving by the pullback by theta J. Okay, and so you can kind of gauge away one of these. You can fix one of them if you like, but not both. Okay, and as we saw in the sort of non-degenerate case, that's key. I mean, that's sort of, you sort of expect that to be the case if you're going to flow these structures. Okay. And yeah, maybe for later, I'll just say, this PDE, I mean, I kind of just dropped it on us, but if you forget the generalized Kähler structure, just forget the I and J. These are basically the normalization group flow equations that arise from this string effective action. And if you forget the J, like if you only have a half of a generalized Kähler structure, which is a Hermitian metric which is plurally closed, then all of that data will be preserved by that PDE, and that's what we call plurally closed flow. And well, kind of amazingly, in any case, it's sort of a non-obvious fact. I sort of said, well, it's just the gradient flow of this F. But you can't actually sort of determine the flows of I and J from the action as far as in at least I think never worked that out. We sort of stumbled upon it from some complex geometry ideas. Okay. But yeah, so the idea is to use this generalized Kahler-Ricci flow to try to construct some Calabi-Yau geometries. Okay. And so what is the prototypical theorem in this area? So this I alluded to earlier. This is Sal's theorem from 1986. So if you have a compact Kähler manifold with C1 equals 0, solution to Kahler-Ricci flow with initial, I should say omega, not G. Anyways, the solution to Kahler-Ricci flow with initial condition omega exists for all time and converges to the unique Calabi-Yau metric in its class. So this is sort of the prototypical thing one would want to prove in this subject. You can't sort of, this is the optimal theorem in this setting. Okay, so we can at least write down now an even more concrete conjecture, which at least covers this closed spinor case that I talked about. So we have a compact generalized scalar manifold in KRI with polymorphically trivial canonical bundles. What I mean here is that both GC structures are defined by global closed spinors. That's what I mean. Then one would expect a generalized Kahler-Ricci flow with this initial data to preserve the generalized Kahler class, exist for all time, and converge to the unique generalized Calabi-Yau geometry in this class, which we know a priori is actually just Taylor, right? So this is in this kind of restricted setting. So this conjecture is only in this restricted setting. And so here's the theorem we prove. So we sort of almost prove it, I guess. This is the same group of collaborators. So if we have a compact generalized Kahler manifold in this setting, we consider to make a further hypothesis. So just assume that MI is already Kahler. Now again, we sort of expect this to be true, but of course we would like to remove this hypothesis. And it has nothing to do with the metric. I'm not saying the metric is Kahler. There's nothing to prove, just that it is Kahler manifold. Okay, then the solution does exist globally. And I just sort of fudge here and I say it formally converges. And what I mean is there are just monotone quantities that tell you if it's like controlled at infinity, it will converge. Okay. So if you could take any kind of limit, it will converge to the right thing. That's what I mean. And then we prove sort of a stronger theorem. So we suppose there exists a generalized Calabi-Yau geometry in the class. Okay. Which again, by this sort of fuzzy definition I gave of the class, which sort of, well, it's not obvious that this is true, even if you're on a Kahler manifold already. Okay, but if there exists one of generalized Calabi-Yau geometry in the class, then we prove it does actually converge. Okay, then it will in fact converge to this metric, which of course again is Kahler already. This is the Kahler Calabi-Yau. Okay. All right, so this largely covers the case of this conjecture, but I mean, I still think it's important to remove these hypotheses, and it might yet be quite hard to do that.
So you're saying that you will always make Kahler.
We know that, or well, sorry, well, we know that if there is a limit, yeah. But a priori, simply asking for a generalized Kahler manifold where both GC structures are defined by global closed pure spinors, I don't know that that's Kahler. I don't think that that's known. Of course, the conjecture suggests that it is, right? And it's sort of a natural way to prove that, but we're of course far from that, right? So both cases 1 and 2 are assuming at least already that the manifold is Kahler, right? But yeah, I mean, it's a nice natural conjecture. And I don't know, like if maybe there's a simpler way to just a priori prove that those hypotheses tell you the manifold is Kahler, maybe, in which case this gets stronger, but yeah. Yeah, I won't really say much about the analysis, or maybe at the end I'll discuss one thing. But I do want to mention 2 corollaries. So yeah, so if I have a Kahler Calabi-Yau manifold, which I can interpret, I kind of write it in this strange way. The point is you can interpret Kahler Calabi-Yaus as generalized Kahler in sort of more than one way. But in any case, I have a Kahler Calabi-Yau, which is part of a generalized Calabi-Yau geometry, GBIJ. Then the generalized Kahler class of that structure is homotopically trivial. Okay? So again, as Vesky alluded to, like, well, as we can kind of see in Marco's talk, like the structure of generalized Kahler classes is quite subtle, non-obvious. But you would hope for something like this to be true, right? That they're somehow contractible. I mean, like in the Kahler setting, we don't even really consider this a question, trivial, proved just by linear interpolation that it's contractible. But here it's a real problem. In any case, we do prove that the generalized Kahler classes of Kahler Calabi-Yaus are contractible canonically by the flow, by the generalized Kahler-Ricci flow. And then to make it even more concrete, there's sort of an interesting statement. Again, there's, I think, all manner of questions about sort of the structure of Hamiltonian diffeomorphism groups that are really quite hard. And there's a statement we get a statement of this kind out of this theorem, okay? So I can fix a hyperkähler manifold, Gij, and I can look at positive Hamiltonians of omega k. So these are Hamiltonian diffeomorphisms of omega k, which satisfy this further positivity condition, which is that if I pull back the I Kähler form and then pair with I, then that's positive definite. So this is, of course, just in disguise the condition for one of these Hamiltonian diffeomorphisms to define a generalized Kähler metric. Right? That's what that positivity condition is that it's defining a generalized Kähler metric. In any case, the connected component of the identity of that group is contractible. That's another way to think about what this corollary above is saying. Okay. So again, I think a priori, like the topology of Hamiltonian diffeomorphism groups is, really a very delicate question. But at least with these extra hypotheses around, we characterize what it is. Okay. Okay, so I guess I still have a little bit of time. So that's kind of what we can prove in the Calabi-Yau background setting. But of course, what about this top surface example? Okay, so of course we want to try to understand this one as well. And I'll just start by mentioning this nice theorem of Godeshan-Ivanov. This is part of what got me going actually in this area. So if you have a compact complex surface where G is only pluriclosed, I'm not even assuming generalized Kähler because it's like half a generalized Kähler. The metric is pluriclosed, Bismuth-Ricci flat. Then you have a very strong characterization. So either H vanishes and it's Kahler-Calabi-Yau, or it's the Bismuth-flat Hopf surface, the one I described earlier. That's the only non-Kähler example, actually, in the compact non-Kähler example in dimension 4. Okay. So with that in mind, we arguably give a sort of complete description of this flow on the sort of only relevant non-Kähler background. And again, for a reason maybe I'll get to explain, the theorem is actually stronger here, which is sort of strange. And I don't even state it for generalized Kahler-Ricci flow. That's underneath this, but I'm really just using the pluriclosed flow here. Okay, so if I have any pluriclosed metric on the standard Hopf surface, then this pluriclosed flow with this initial data, any initial data, exists for all time and converges to the Hopf surface, to the Hopf metric. Okay, to this standard Hopf metric. Okay, and yeah, and this is joint with my student Josh Jordan and Mario Garcia Fernandez. Okay, so yeah, so we prove a stronger result. And then again, corollary here. So like I said, this is kind of more general than generalized Kahler-Ricci flow, but of course that's a special case. And so a corollary here is that again, and here there's actually no, I don't have to sort of quibble about this connectedness issue actually, right? Because I'm really just taking any generalized Kähler structure of any kind, and I show that the flow canonically contracts it down to the standard structure. So the entire space of generalized Kähler structures on the standard Hopf surface is contractible by this Ricci flow to the standard structure. Okay? And it's because, well, in any case, the reason it's stronger is sort of in the guts of the PDE argument. Okay. Yeah, let me maybe invert the order of this. Let me just maybe skip this for a second. And let me actually, say how the proof of this last theorem goes, because it's a really, I think, beautiful. I think when I first started to understand the structure behind this is when I really got sold on generalized geometry, I think. So hopefully I can sell you on it too. So the analysis in a crucial way relies on sort of reformulating the flow using what are called holomorphic Courant algebroids. So again, Mark will discuss these in his talk. And in particular, sort of more or less building on an observation of Bismuth, who sort of, he didn't really sort of carry it all the way through, but he was basically doing holomorphic Courant algebroids in disguise, more or less. And so let me just describe what it is. So if you're given a pluriclosed metric omega naught, consider the holomorphic vector bundle T10 plus lambda10, but we give it a twisted d-bar operator. So that already has a d-bar operator, but we consider this so-called twisted d-bar operator. So it's twisted by the metric omega naught. And so how does it act on a vector plus covector? Well, it's the standard d-bar operator, but then plus I times the interior product of X with del omega naught. So that's interpreted as a one form with values in one forms. Okay. So we have this twisted d bar operator, and the fact that d bar squares to zero, that this d bar squares to zero, is exactly the condition that it's very close. Okay, so that's what tells you that this thing is actually integrable. Now I'll take another pluriclosed metric and assume that, so a pluriclosed metric defines a torsion class in H21, and basically I'm just assuming that the torsion class is the same as the one that defines the d bar operator. So del omega minus del omega naught is d bar of some 2-0 form beta. Given that data, I can define a Hermitian metric on Q. Now, again, I think for those of us steeped in generalized geometry, this formula doesn't look maybe so surprising. But what it is just the standard metric that you would put on like the tangent and cotangent bundle, but then conjugated by a B field transformation using this beta, I times this beta. Okay, so you get this is a Hermitian metric on this holomorphic vector bundle. Then the kind of amazing observation of Bismuth, and again, this came from, he was purely doing like complex geometry. He wanted to prove a generalization of the index theorem on non-Kähler manifolds. His observation, well, it's really even more than what I write here. He observes that the so-called Bismuth connection of the metric is sort of canonically identified with the Chern connection of G. So G is a Hermitian metric on a holomorphic vector bundle. It has a canonical Chern connection that is sort of canonically identified with the Bismuth connection of little g. Okay, so somehow this big G is sort of recapturing the geometry of the Bismuth connection. And then, yeah, going further, we let S, for me, SG is the Hermitian-Yang-Mills operator. Okay, so you take the Chern curvature of big G, and then if you trace on the form piece using the metric, you get an endomorphism of the bundle. The vanishing of that Hermitian-Yang-Mills curvature is exactly the same as the vanishing of the Bismuth-Ricci. Okay, so this sort of Einstein type equation we thought of on the manifold is a Hermitian-Yang-Mills type equation on this bundle. But you should keep in mind, of course, that usually when we think about Hermitian-Yang-Mills, we think of a metric on the base as being kind of part of the background structure. But here that's not the case. So the metric defining the trace is, of course, the one and only metric you have in the story anyways. It's not like the omega naught trace or something. That it's all defined using the same metric. Okay, and yes, I just repeat the metric and the one-third metric, and then the kind of amazing point, you can just take it one step further and take a time derivative, and that formally the sort of pluriclosed flow written in terms of omega and beta. So here omega evolves by like the 1-1 part of the Bismuth-Ricci, and beta evolves by the 2-0 part. If you let them evolve that, this just is the pluriclosed flow I mentioned before. What you see again is sort of formally Hermitian-Yang-Mills flow. But I say formally just to emphasize again this point that the metric defining the trace in the definition of S is also flowing. Okay, so you cannot just sort of plug into all the nice theory you have for Hermitian-Yang-Mills flow. Okay, and then yeah, well, once you know this, the proof of this theorem of convergence on the Hopf surface is almost trivial. I mean, if you know well the proof of Yau's theorem, I mean, you can just start computing using this generalized picture. You kind of have to know that it might be the right thing to do in the first place, but the computations are actually very simple in this picture. And so in particular, you can apply the heat operator to say the trace of the metric against some background, and it has a sign. And this is using the flat background geometry you have on the Hopf surface. And then moreover, like one of the key aspects of Yau's theorem is the so-called C3 estimate, which is sort of related to the Evans-Krylov estimate. So if you have uniform ellipticity of the equation, so if you have like upper and lower bounds for the metric, you want to know, is it like C2 alpha or C3? And in the case of Monge-Ampère, in Yau's theorem, the sort of modern proof, and this is also what Yau basically does, but he doesn't quite say it this way, is you're just estimating like the Chern connection of your Kähler metric against the background using the intrinsic norm. And then that's what you do here. So now basically you estimate the Chern, that's what this upsilon is. So upsilon here is the difference of the Chern connections of your moving metric with a fixed background. And sort of miraculously, you have sort of a sign for the highest order piece. And then in the special case of the Hopf surface, even the sort of lower order background terms just completely drop out. But sort of underneath this, not on the Hopf surface, are like very clean evolution equations for both of these quantities that let you prove something like Evans-Krylov theorem for Gualtieri flow and generalized Kahler-Ricci flow. Yeah, so I guess like for me, I started to see this structure and like the connection to generalized geometry, and I mean it's just absolutely amazing to me. I mean, if you actually think about writing down the Chern connection of that big G in terms of the classical data, I mean it's an absolute nightmare. I mean, you would never see it in a million years. I would never have seen it in a million years. But somehow, once you think in a generalized way, it's actually relatively easy to prove it. So yeah, so this is how we get the flow in the case of the Hopf surface. And I guess I still have maybe a few minutes. I'll just go back and say that there's even sort of more to what we ought to mean by the Calabi-Yau story. So yeah, and this is of course relevant from the point of view of generalized Kahler-Ricci flow as well. So sort of more generally, so I kind of lied before and I said the Euler-Lagrange equations for this F functional were these like Bismuth-Ricci flat. Well, that's not really quite true. What really the Euler-Lagrange equations are what I write here. I call it generalized Kahler-Ricci soliton. So Ricci minus 1/4 h squared plus some generic Lie derivative term is 0. And d star h minus the interior product of grad f with h is also 0. So again, these are some kind of like gauge modified Bismuth-Ricci flat equations. We can sort of ask, well, what about these? Because again, from the point of view of the flow, this is really what the long-time limits are. And of course, we know well, like the theory of Taylor-Einstein metrics on Fano manifolds is really very much also tied up with the theory of solitons, in fact. And it turns out that these things do exist. So, and here again, I focus on the case of complex surfaces. So building on a lot of prior work, including Kodaira classification, work of Telemann, Apostolov, Gualtieri, you can prove that solitons can only exist on diagonal Hopf surfaces. So the Hopf surface that we've seen throughout this week is kind of what I would call the standard Hopf surface. You can have more general Z actions on C2, I mean, you have more general Z actions, and you get, well, and then one important subclass are the diagonal ones, where at least the action preserves the two factors. So they can only exist on these, and then it turns out, oh yeah, good, I write the formula here. So this is what I mean in general by a diagonal Hopf surface. Okay, and then the theorem, again, of Vesti, myself, and Yuri Ustinovsky, is we can give a complete classification of these things in 4 dimensions. Okay, so this is, we can think of as building on the Godeshan-Ivanov result. So we fix compact generalized Kahler-Ricci soliton, then precisely one of the following holds. So either Mi is Kahler, and then G is just Kahler Calabi-Yau, and then I is plus or minus J, or there's, well, sort of 2 classes of examples. So MGIJ is an odd type generalized Kahler structure, which here just means that the 2 complex structures commute as endomorphisms. Mi is one of these diagonal Hopf surfaces, and the metric and complex structure are unique up to automorphism and scaling, or it's an even type generalized Kahler structure, which with all the same characteristics. And yeah, I guess the way I think of theorem, of course, we do construct them as well. There is a soliton on every one of these Hopf surfaces, and it is unique. So up to scaling and automorphism. And then what's even kind of more amazing is that actually the metrics on the metrics in case 2 and 3 are actually the same. So for every choice of parameters alpha and beta, there's this one metric which is generalized Kahler in 2 ways. So it's actually compatible with 3 complex structures. And that's actually what's also happening on the Hopf surface, right? I mean, the Hopf surface is, well, sorry, what I mean is the standard Hopf surface. So in the standard Hopf example, right, the same metric, this phi invariant metric on SU2 process 1 is compatible with two kinds of generalized Taylor structures. One of commuting type and one of the type we saw. And that phenomenon kind of persists for all of them. And maybe I just, instead of describing the geometry of these things, I just say it forms a smooth family with the standard structure as the moduli passes through the standard case. Okay. So okay, thank you for your attention.
Thank the speaker and any further questions or comments?
So what's the difference if you square dimensional overlap?
Yeah, so yeah, this theorem that I mentioned, it basically holds, so for any business flat background, we can prove the global existence and the convergence to some business flat metric, but somehow, embarrassingly, we can't actually prove even the uniqueness of business flat geometries in a fixed FE class. There's some kind of subtle variation there, but the PDE is fine. The PDE does the right thing.
So what about if you put fundamental group?
Oh yeah, that's of course fine too. Yeah, the finite quotients you just let them flow. Yeah, that's fine. Yes.
Yeah. You focus on the one route is solve over like C1 negative.
Oh, of course. Oh,
So
I mean, yeah. So, right. So there, of course, yeah. I mean, the PDE, of course, makes sense. I mean, both. Well, like the political still makes sense in all of those cases, and the expectation, which can be proved in some cases, is of course that it just behaves exactly like Kahler-Ricci flow. So it exists globally, and when you flow down, you get convergence to the Albany-Allen metric. Yeah. But and yeah, that can be proven in some, but not all cases. Yeah.
the comment, I guess C1 negative means there's no
Right. In fact, yeah, I think the C1 negative, there's not too many interesting generalized scalar structures. There, it's really the more interesting case would be like very close flow, where you have lots of metrics. But yeah, I guess in fact, I think the only real case that you have are commuting type structures on like products of high G's and non-surfaces. I think that's the only case that really relies on for generalized scalar.